We're not going to talk something about transition from decelerated to accelerated expansion of the universe. Uh, since the immediate observational evidence for the faraway supernova is being lower than anticipated luminosity, one might wonder whether there's a more mundane astrophysical explanation. Maybe this luminosity diminution is brought about not because supernovae are further away than expected, but due to absorption by some unknown interstellar dust. Because the dust we know usually have character frequency dependence, but maybe there are some other we don't know yet. Some dust that doesn't have this kind of familiar frequency dependence, and or some yet unknown evolution of the supernova themselves. Supernovae's intrinsic luminosity were smaller in the cosmic past. It's possible. But all these scenarios would lead us to expect that the brightness of the supernovae at even greater distance, even further away, so it must be further back in time, will continue to diminish, right? Because the more dust that pass through and also even older. So for the case of accelerated universe, on the other hand, at an even greater distance, this diminution of luminosity will stop and brightness will increase. This so because we expected that the accelerating epoch was preceded by a decelerating phase. Remember, dark energy density should be rolled into center scale change basically. It's a constant throughout cosmic time. While the matter and radiation energy density scales like matters like 1 over a cubed, radiation 1 over a to the fourth power, which should have been more important in the earlier times. Smaller a, these density would be higher. This earlier universe could not have been dark energy dominated, so it must be in a decelerating expansion. The fact that the acceleration must precede by deceleration, so the Hubble curve, there should be a bulge. Okay, here's the Hubble scale factor as a function of cosmic time, and normal case, for example, for the flat universe, it should be, it just goes like this, uh, and but accelerator will expand. So if you start with bending downwards and then turns into transition going bending upwards, so there will be a bulge. Okay, and so this will be the case of a flat universe with a cosmological constant. Actually, there are now a few years after the discovery, many people obtained the evidence for such a bulge. Okay, so really this discovery of accelerated universes. So we're going to talk about at what time when this transition took place. Uh, so let's estimate the ratio at which the universe made this transition. Remember we talked about in one of the break exercise 23.2. By the way, last time was a 25 point. It should be 23.2. Deceleration parameter uh, can be written in terms of density. This is just it turned out to be just another form of second Freeman equations, and radiation being negligible, so therefore the sum over different just really only talk matter and the dark energy, and when I equal to m, this equals 0, so it's just this, and this factor 1/2, and then when I is equal to lambda, uh, this is minus 1, so therefore this is minus 2, just cancel to get this minus sign here. Okay, and then you plug in the scale dependence. Matter scales like 1 over a to the cubed, and uh, lambda is constant. So after putting this scale dependence, we have this. So this deceleration parameter as a function of time is given by this expression. Now transition from deceleration, which q from plus 1 because decelerating, so q positive to negative occur, of course, and we define the transition time to when q equals 0. Q equals 0, this equals 0 means that a cubed equal to uh, omega m over omega lambda. Okay. So it's a very simple expression. And you plug this expression a cubed over this into here. So a cubed equal to omega m over 2 omega lambda. So this just turns to be, this factor become 1/2. This factor 1 plus 1/2 is 3/2. And so you just plug in. You get this point through cosmic time. Plug in the Hubble time to 14.5 GeV, about 7.6, so roughly 8 billion years after the Big Bang. So this is a time when the expansion, after spending 8 billion years slowing down, starts speeding up again. It has been accelerating for the past 6 billion years. Now, in terms of cosmic time, this happened only recently because, especially, the time we should think in terms of logarithm scale rather than linearly. So the cosmic, so we say that people wonder why this happened so recently. Okay, so why the transition time coincide with our present time? And basically, the question is the same as why is the matter density so close value to the dark energy value? They're both around. In astrophysics, in physics, they could be so completely different. So we're talking about this picture of history of the universe, start from the beginning singularity and inflation, and then expand, and then to be expanding but slowing down, but then starting. So this transition is really very close to the present time. So it really started only very recently. Oh, here's the lesson we learned from lecture 29. Since we have a second cosmological constant of dark energy, which is much smaller than the first one involved in the explosion, which we call inflation. The dark energy is a major component, about close to 70% of our energy budget, and compared with 30% for matter, leading to a total omega equal to 1, consistent with a flat spatial geometry. Being a negative pressure, hence a repulsive gravity, the dark energy brings about an accelerating universe. And first observed through the redshift measurements of supernovae, the Hubble curve bends upwards. And the matter dominating a flat universe has an age 2/3 of Hubble time, but dark energy lengthens it to 13.8 gigayears. Actually, very close to. It's the acceleration is cancelled, and leaving us cosmic age is roughly the same as like an empty universe. And acceleration was preceded by deceleration, with transition time about 8 gigayears. So the last lecture we're going to talk about the lambda CDM as the standard model of cosmology. We summarize it. Still, we do not know the physical origin of dark matter and dark energy. The most natural idea for dark energy is simply the quantum vacuum energy. This can't account for all its property, except the theory would suggest a size that's more than 120 orders too large. So some fundamental physics missing.